Good morning and respect to the teacher. And hello, everybody. We are from Team 8. My name Chatola with my teammate Duong Mandit and TGO. Our project is a CPU scheduling simulator. The purpose is to show how an operating system decide which process get to use the CPU and when. We build five scheduling algorithms such as first come first serve, SJF, SOT, round robin, and LFQ. We measure on three things for each algorithm, such as waiting time, turnaround time, and response time, to see which algorithm work best. We have two versions of the simulator, a Python command line and a website-based version that run in the browser. So as you can see, we have here's the our project, the main file. We have index.html, which is the web UI. We have the UI to uh, use that algorithm to simulate, and we have scheduler.py, which is the Python simulator, and the process dot CSV, a sample input data. The program work like this. You enter the process, pick an algorithm, and the simulator run it and show you the Gantt chart and the result of the result table. For the next part, I will give to my teammate.
So hello teacher and hello everyone. My name is Lucy and now I'm going to walk you through the two most complex algorithm of SRT and LFG. And at the end, I'm going to run the live demonstration of both of these algorithms. Okay, so here is our SRT implementation, or we can call it the shortest remaining time, which is the primitive version of SJL. Okay, so here, this is the key challenge with the SRT is handling preemption accurately. So one approach would be to simulate every single clock tick one by one, but it is very slow. So instead of doing that, we use the event-driven approach to make it run smoother and faster. And here on this line. Here on this line, the code will look at the future arrival time of the process that have not finished yet. So we then calculate how long the current process can be run before the next event, which is either a new process arriving or the current process finishing. So we take the minimum of those two values, and this means that the clock jumps directly to the important event, which makes the simulation both accurate and efficient. And when the new when the new process arrives with a shorter remaining burst time than the current running process, the context switch will happen immediately, so that we track this by updating the remaining burst time of the current process and putting it back into the pool. And here at this line, we also record the start time of each process, the first time it gets to the CPU. So this is used for calculating the response. Okay, so that's all for the SRT. Okay, so right here I'm going to show you the MLFQ implementation, or we can call it the multi-level feedback queue. Our MLFQ has three queues. So the first queue is zero. Should we set it as queue 0, which is the highest priority using round robin with a quantum of 2. And queue 1 is the medium priority using the round robin with a quantum of 4. And for the third queue is the queue 2. is the lowest priority using the first come first serve with no level. Okay, and all the process and all the new process that start in the queue 0 here. You can see that when a process arrives, it adds directly to queue 0. So if a process uses its entire quantum without finishing, it will get moved down by one level. So for example, if a process that used its full 2-unit quantum in queue 0, so the queue 0 will get moved to queue 1. Okay, and here is the aging mechanism at the start of every scheduling decision. So here at the start of every scheduling decision, we check all the process in queue 1 and queue 2. So if any process has been waiting longer than aging threshold, which is the default to 10 unit, it will get promoted back to the queue 0. This prevents the starvation where the long process could stay stuck forever. Okay, and the wait timestamp is reset every time the process is requeued or promoted, so the counter will restart cleanly. Okay, so that's all about the algorithm. Okay, so now we have finished with the code, so I'm going to move to the demonstration. So here is our website that we have created, and on the left side right here is the process that we can adjust or put any value that we want to calculate. So I have already put the number, so I'm going to just choose the option right here. We have FCFS, which is the first come first serve, and we also have shortest short first, shortest remaining time, with which that we will demo it soon, and the round robin, and the last one is the MLF or the multi-level feedback shoe. So now I'm going to start with the SRT. I'm going to click on it and I will start running the simulation. Okay, so now we can see that the Gantt chart display the order of the process of the CPU, and down here is the table that lists the value that we have put in the process, and also we also got the average answer of the wait time, the turnaround time, and also the response time. So that's it for SLT. I am going to move it to the MLQ, which is our second algorithm that I will demo for you. Okay, so when I click the MLQ option, the algorithm section here will display the Q1 or 2 unit, and the Q2 we have 4 unit, or we can set it more than that or less than that. And for the aging threshold is 10 by default. So okay, so the average, as we can see in this table, the average response time is 4.25. so the best of all 5 algorithm, because every process get its first CPU slide very quickly, but the waiting time is higher at 5. So it's because the process keep taking turn instead of finishing one at a time. Okay, so that's all about my demonstration, and I will let my friend explain further.
Hello teacher, I'm KGO and I'm from Team 8, and I will explain the result of our CPU scheduling simulator. So I will run the simulations, as we can see here. So we can see, let's take a look at the FCF. So first come first servers algorithm is simple but the slowest. Why? Because the reason it's slow, because like if we have a process that take a long time and another process behind it, it takes short, but the longer process come first. So yeah, it's not good. It's hold the older process like P3, it's hold P4 on the back. So the P4 process who should have complete still wait till P3's process completes. It's not a good. Yep, and this is called convoy effects. So, and if you're looking at round robins and MLFQs, it have a higher waiting times and higher turnaround times. Um, yeah, because a process keep taking turn small slides instead of finish one at a time. And we can look at the Gantt chart here. It's taking small turn every 2 seconds. It changes from P1, P2, P3, P1, P4, P2. It changes every 2 seconds. So and FMLFQ is also the same. Yep, it's take turn for the algorithm for the CPU to complete the process. So yeah, and if looking at FRTs, we can look at their FRT turnaround time. It has the lowest turnaround time. We can call it the fastest process algorithm. Even the wait time is the fastest. It has the lowest waiting time because it take the shortest job first. Yeah, that's why it process fast. Um, but so but for response time, MLFQ wins. Let's talk about round robin and MLFQs. For response time, MLFQ win with 1.25 and round robins is 2 seconds. So this means that every process gets its first CPU slide very quickly, which is important for interactive apps. So if you want fastest competition, use SRTs, but if you want every process to respond quickly, use MLFQ or round robins. So in conclusion, no algorithm is perfect for everything. Simple ones like FCFS are easy but not efficiently. Complete one like round robins or MLFQs are real operating system used because they handle all types of process well. So this is Team 8 CPU Scheduling Simulator projects. Thank you for watching. Goodbye.